Today's lesson is about statistical power. In an earlier lesson, we talked about a contingency table and the types of errors that can be made in hypothesis testing. Again, when we were looking at it, we had on the side in rows whether or not the HO is false, that is, therapy actually does work, or on the bottom row, the HO is true, that the therapy really is ineffective. In columns, we have our decisions. We could decide to reject HO and conclude that the therapy works. Or we could decide that there is not enough evidence, and in that case we would fail to reject HO. Now let's look at the situation when, in fact, if therapy really is ineffective and we decide that there's not enough evidence, we fail to reject HO and conclude that there's not enough evidence, then we're correct. On the other hand, if our decision is to reject HO and we conclude that the therapy works, when in fact the therapy is ineffective, then we've made a type 1 error. Again, this is review. The part that I'm adding to this is that the probability of a type 1 error, there's really two types. One is called an a priori probability, and that's given to us by alpha. That's the most we're willing to risk being wrong. And we usually set that at a 0.05, but it could be set at a 0.01, sometimes at a 0.1, but most typically at a 0.05. Another probability of a type 1 error is based on the data. That's an a posteriori probability. That is, based on our data, how likely is it we would be making a type 1 error given the data that we got. Now notice that if in fact therapy is ineffective, we're either correct or we've made a type 1 error. It's impossible to make a type 2 error if the therapy really is really ineffective. And the reason for that is a type 2 error is believing a therapy works is in not realizing a therapy works when it really does. And in this case, it doesn't work, so we can't make a type 2 error. Let's look at it at the other, if the truth is that the therapy works. Well, if in fact the therapy works, that is, if the HO truly is false, and we fail to reject the HO and determine that there's not enough evidence, then we've made a type 2 error. A type 2 error. And the probability of a type 2 error is given by beta. On the other hand, if therapy works, if the HO is false, and we reject HO and determine that therapy does work, then we've made a correct decision. And the probability of that is called power. And that's what we're here to study today, is power. How do we find out how powerful a study is to discover something works when it really does work? Now, notice, by the way, if therapy works, it's impossible to make a type 1 error, because a type 1 error is thinking a therapy works when it doesn't. And in this case, it really does work. So it's impossible for us to make a type 1 error when, in fact, the therapy works. Let's look at the contingency table in a slightly different way. Imagine instead that we decide therapy works. We decide therapy works and we reject HO. Well, if in fact the HO is false and the therapy does work, then we're correct. But if we decide to reject the HO and conclude therapy works, when in fact therapy is ineffective, that the HO is true, then we've made a type 1 error. And again, the probabilities of type 1 error, there's two types, an alpha, which is the a priori probability, or there's the p-value, which is the a posteriori probability, the probability based on our data of making a type 1 error. But notice, if our decision is that the therapy works, if we've decided to reject HO, we're either correct or we've made a type 1 error, but it's impossible to make a type 2 error if we've rejected HO. On the other hand, if we decide there's not enough evidence and we fail to reject HO and conclude there's not enough evidence, and if in fact the HO is true, that is, that it's purely coincidence if our subjects differ from the expected value. If that's true, the therapy is ineffective, then we've made a correct decision. On the other hand, if we decide to fail to reject the HO and conclude there's not enough evidence, when in fact the HO is false, the therapy really does work, well then we've made a type 2 error. And again, the probability of that is given by beta. Now notice, if we decide to fail to reject the HO and conclude there's not enough evidence, we're either correct or we've made a type 2 error, but it's impossible for us to have made a type 1 error. How do we calculate power? Well, to date, we've been using pictures of distributions to understand whether to do our hypothesis testing. And I've been telling you that if you draw the pictures, the problems will work themselves out, as long as you draw the pictures correctly. But we are now moving from a one-picture problem to two-picture problems. So our first picture that we have to draw is a picture when the null hypothesis really is true, that the therapy has no effect. And in that picture, we then draw a rejection region when we'll mistakenly believe therapy worked, even though it didn't. And we find a cutoff value for that rejection. That's what we need to take to the next picture. The next picture I call the truth curve. This is if in truth the therapy works. And we know the truth somehow. Then what we do is we draw that curve, we draw the rejection region based on the cutoff value we got in our first picture. And then we find the probability of getting that rejection region given that in fact the therapy works. It sounds harder than it is, but it's plenty hard. So let's take a look at this a little bit further. If a treatment doesn't work, that is, we're drawing the null hypothesis of when the treatment does not work. The first thing you do is you draw a rejection region. Now, if we've got an alpha of 0.05 in a two-tailed test, half of that 0.05 would go in the left tail, and another half would go in the right tail. Now, if we got data, if our sample data fell in either of those tails, we would conclude that therapy works. But since this is a drawing of when therapy doesn't work, when we're in those areas, we are incorrect. Those are our alphas, those are our errors. If we don't fall in those, if we fail to reject HO, then in this graph we would be correct, because this is a graph of when HO is false. The therapy does not work. So what we do is once we have our areas here, We have to find what value of z would lead us to reject HO. Now, another type of test we could do is a one-tailed test. In a one-tailed test, we'd put our entire alpha in either the left tail, if it's something we wanted to reduce, or in the right tail, if it was something we thought would be increased. Now, typically, I don't like one-tailed tests. I encourage you to use two-tailed tests most often. But in today's problems, we're going to use one-tailed tests just because they're much easier to calculate power from. And the principles you learn about power from a one-tailed test are the same principles that would apply to a two-tailed test. So we're just going to use one-tailed test in this case because it's easier. So if I have put my entire percentage in that tail, or I could put it in the other tail, but if it's in one tail, the entire 0.05 goes there. Now, once I had my cutoff values, percentages, I need to find the z-score and also the raw score that would give me, actually the raw score, where I would believe my therapy works, even though in this case it really does not. And you know how to go from a percentage to raw score. Well, you can't get there from there. So what you have to do is go from a percentage to a z. And we do that by using the cumulative probability column of the z table to find the z. And once you have the z, you can use the French equation to go from the z to the raw score. Remember, the French equation is a raw score equals a mean plus z standard error. The raw score equals a mean plus z standard error. So the next thing we do is we draw the truth curve. And then we put on that truth curve the rejection region that we determined from our previous graph. And then we find the probability of that rejection region. So we draw a normal curve, but now we have to put the new mean, because if our therapy works, it's going to change the mean. If our therapy increases whatever it is we're measuring, then we're going to have a higher mean after therapy. If it's something that's supposed to decrease the behavior, then we'll have a lower mean after therapy. So here you have to put your new mean. Then you have to put the critical mean, the value where you think the therapy works, where you will reject the null hypothesis. In this case, rejecting the null hypothesis is the correct decision, and failing to reject the null hypothesis is the error, and it's beta. It's a type 2 error. So we know how we can find that. If we've got our raw score, or if we've got an X score, well, we can't get to the percentage directly. So we have to go from the raw score to the z, using the equation that z equals the sample mean minus the population mean divided by the standard error. And then once we get our z, we can use the z column of the z table to find the cumulative probability. All that sounds probably harder than it is. Let's try a problem. The Herrera lunacy diagnostic test, that HLDT, has a mean of 120 and a variance of 142. If you develop a pill that would decrease lunacy by 6 points, and you test it on 7 patients, how likely are you to discover that your pill works at the 0.05 level? So let's extract the information out of there. The population mean is 120. The population variance is 142. If we take the square root of that, we know the standard deviation is the square root of 142, which is 11.9164. Our alpha is 0.05. Yeah, it tells us alpha is 0.05, so that's that. The n is 7 because there's 7 patients. And the effect is we expect a decrease of 6 points. So that's our problem. The first thing we're going to do is draw the null hypothesis. I'm going to put our information here in the top right corner so it's easy for us to remember it. We draw a normal curve. We put a line down the middle. Now, if the treatment doesn't work, then the patients that have had the treatment should have the same mean as the patients who have not had the treatment, which would be 120. Our alpha is 0.05, and we're expecting to decrease the behavior, so we're going to put our entire 0.05 in the left tail. And what we want to know is what's a cutoff value? What is that raw score where we're going to, if below which, if we get that sample mean, we're going to think that the treatment works? Incorrectly, according to this graph, because this is when it doesn't work. Now remember, to go from the percentage to the score, we have to first go to the table and find the z. If we go to the table to find the z score for 0.0506, or 0.0500, we'll find it's halfway between negative 1.64 and negative 1.65. So I'm going to go with negative 1.645, which is halfway between those two. Now we can go from our z-score to our raw score using the French equation. First, we have to find our standard error. And remember, our standard error is a standard deviation, which we now know is 11.9164, divided by the square root of n. Which we know is 7. And when I calculate that, I get the standard error is equal to 4.5040. So now I can use my equation. I can take my standard error times the z-score and add that to my mean. That gives me negative 7.4091 plus 120. And that ends up being 112.5909, and I put that in my graph. That's also the number I'm going to carry to the next picture. But I'm also going to carry my standard error, because that's not going to change, and I don't want to have to calculate it twice. So now I draw my new picture. Now this is when the effect size is negative 6. This is when it really does work. So if the mean before treatment is 120 and it reduces everybody's score by 6 points, my new mean should be 114. Now I say, where would 112 be? And it would be on this side in this case. And I'm looking for the area that's below 112.59. That'll tell me the probability of getting a sample mean that's in that area. Well, that's my rejection region. And by the way, in this case, rejecting is a correct decision because this is when the therapy really does work. So to go from the score, I'm going to first go to the z, and then I'll go from the z to the percent or probability. So first we'll do our z. We're going to take our standard error is still 4.5040. And we're going to take our cutoff value of 112.5909 minus the mean, but notice it's a new mean, it's 114. And we're dividing that by our standard error. That gives me a negative 1.4091 divided by the standard error. And that gives me negative 0.31. When I go to the z table and I look up negative 0.31, I get 0.3783. So that is the probability of correctly rejecting the HO when the therapy really does work. Or you could say the power is 37.83%. So that means if I really did have a therapy that really did reduce this measure by 6 points, the chance that an experiment using 7 subjects with this standard deviation is only 37.83%. So most of the time, even though the treatment works, an experiment like this would fail to reject HO, and you would conclude there's insufficient evidence. So that's how you do this kind of a problem. And we will now move on to example 2.